Doing today? We are going to take derivatives of things other than e. So, for example, let's do our little recap. So if I give you y is equal to e to the x, well, the derivative of y is pretty easy. It's just e to the x. But what if I gave you y is equal to 2 to the x? How do I take the derivative of that? Right? So that's kind of the question. How do you handle bases when they're not e? When it's e, it's easy, right? Derivative of e to the x is e to the x. I could put happy faces here, and we'll talk about chain rule. But how do we handle it this way? Now, what I'm about to do is the full explanation of where the rule comes from. You don't have to do this. In fact, you don't have to even copy it down. I would like you to watch just so you know where it comes from. So, when you don't know how to handle when there's a variable in the exponent, you never will. And since you don't know how to handle a variable in the exponent, we have got to figure out a way to get the variable out of the exponent. How we do that is we're going to use logarithmic differentiation. So that simply means I'm going to take natural log of both sides. And what that lets me do, because I've got a log here, that lets me bring this exponent down in front. So when I take log of both sides, that's going to give me natural log of y is equal to x natural log of 2. And just keep in mind, finding y prime is the exact same thing as finding dy dx. So we're looking for dy dx. And with logarithmic differentiation, it's basically you're doing implicit differentiation. So we're going to take the derivative of both sides. So the derivative of natural log of y, that's going to give me that 1 over y, dy dx. And let's talk about the derivative of this. So what's the derivative of x natural log of 2? Well, natural log of 2 is a number. So this is a number times x. So if I said, what's the derivative of 7x, everybody in here say, well, the derivative of 7x is just 7, right? So when you have derivative of a number times x, the answer is just whatever the number is. So when I have a derivative of number times x, the derivative of that is whatever the number is, which in this case is natural log of 2. Again, I want to solve for dy dx, so I'm going to multiply both sides by y. So I end up with dy dx is equal to natural log of 2 times y, but I don't want y in my final answer. With logarithmic differentiation, you want to replace that y with what y equals. So I end up with dy dx is equal to natural log of 2, and y was 2 to the x, and so I end up with natural log of 2 times 2 to the x. Now I don't really care if you write this part down. I do care if you write this. So I need everybody, we started with y equals 2 to the x, and we did some stuff, and then we found out that the derivative of that is natural log of 2 times 2 to the x. So that's important to write down. Now I want to compare that to so here's our summary. So the derivative, if y is equal to e to the x, then the derivative of y is equal to e to the x. If y is equal to 2 to the x, the derivative of y is equal to 2 to the x and a natural log of 2. What's the takeaway? All right. When you take the derivative of an exponential function, you just get the exponential function, right? And the same thing kind of works if it's not e. When you take the derivative of 2 to the x, notice we got a 2 to the x. I started with a 2 to the x. The derivative is a 2 to the x. But because it's not e, because it's not e to the x, we have an adjustment. And in this case, the adjustment is natural log of 2. In general, the adjustment is natural log of whatever the base is. All right? So let's sort of compare when they're a little more complicated. If I give you y is equal to e to the x cubed, and I give you y is equal to 2 to the x cubed, well, how do we take the derivative of e to the x cubed? Well, derivative of e to the x cubed is e to the x cubed times 3x squared. The derivative of 2 to the x cubed is going to be 2 2 to the x cubed times 3x squared. See how I'm treating this exactly the same way I treated e. But the difference was, because it's not e, right? Because I'm dealing with a base that's not e, the base that's 2, I need an adjustment, and my adjustment is going to be natural log of 2. All right. So when taking the derivative of exponential functions, right, the way you handle it is exactly the same way you handle it if it's e to some power. The difference is, if it's not e, you need your adjustment, and your adjustment in this case is natural log of 2, because this was base 2. So your turn. I want everyone to write these down and do them. So we're going to give y is equal to e to the sine x plus x squared, and then y is equal to 5 sine x plus x squared. It's a squared. And I want everyone to find the derivative of these two, and once you've written the derivative, do the electronic hand raise so I can see who. Okay, about 15 more seconds. All right. So, derivative of this first one, e to stuff, is going to be e to stuff, which is sine x plus x squared, times derivative of stuff. And so the derivative of sine x plus x squared is going to give me cosine x plus 2x. And you're done. Derivative of 5 to stuff, well, derivative of 5 to stuff is going to be 5 to stuff, which is sine x plus x squared, times derivative of stuff, which is cosine x plus 2x. Right? So what I'm doing is virtually what I did over here, except because I'm not dealing with e, I need my adjustment, and my adjustment is going to be natural log of 5. Let me write that a little cleaner. So that's going to give me natural log of 5. Usually they stick this next, so that's going to give me cosine x plus 2x, and then times 5 to the sine x plus x squared. And they usually put natural log of 5 in parentheses. And so this is your answer. All right. And the big idea is, you want to make sure that when you're taking a derivative of an exponential function, you're pretty much doing the exact same thing you did when it was e. The only thing different, if it's not e, is you need your adjustment. And your adjustment is going to be natural log of whatever the base is. If you were to look in your textbook, they would say, given y is equal to a to the x, or a to the u, and they don't use x, they say a to the u, then y prime is going to equal natural log of a times a to the u times derivative of u. This is kind of this is the official, this is what most textbooks have. Actually, I think probably what most textbooks would have is they would say dy du is equal to, oh no, that's, yeah, and so that's going to be natural log of a times a to the u times du. I think that's what most textbooks have. And I mean, I could give you the rule, but and then start doing examples. I'd rather you have these two things written out, like you've actually done these two problems. And so with these two problems, you can kind of see how what you're doing when the base isn't e is you're doing the same thing. You just got to remember to stick that natural log of 5, or natural log of whatever the base is. All right. So actually, while we're taking derivatives of exponential functions, I've got 4 problems I want you to do, and it's a pretty good summary of derivative of exponential functions. So here are 4 problems. So problem 1, if y is equal to e to the e. Problem 2, if y is equal to e to the x. Problem 3, if y is equal to x to the e. And then problem 4, what if y is equal to x to the x? What I want everybody to do is take the derivative of these 4 things and do the electronic hand raise when you've taken the derivative of all 4. Okay, I'm going to give you about 30 seconds. And to be honest, question 4 isn't really fair. So if you're having issues with question 4, there's a reason. If you're not having issues with questions 4, you may want to pay attention to how we do question 4. All right, so e to the e, that's a number. 2.718 to 2.718, that's going to be a number, and the derivative of all numbers, derivative of all constants is 0. That was pretty easy. Problem 2, well, derivative of e to the x, well, that's just going to be e to the x. So question 1 and 2 aren't so bad. Question 3, x to a power. Well, you know, if I'd given you x to the 7th and said take the derivative of x to the 7th, you would tell me 7x to the 6th, right? That's what you'd tell me, right? X to the 7th, you'd tell everybody in here would say, oh, that's 7x to the 6th. What did we do? We brought the exponent down, and then we subtracted 1. We're going to do the exact same thing here. Turns out the derivative of this is going to be ex. Well, you got to subtract 1. How do you subtract 1? You literally just write e minus 1. Right? Because, I mean, that's what happened here. It was 7x to the 7 minus 1. We just happened to know that 7 minus 1 was exactly 6, and so that's why we write it. We're going to do the same thing here. You know, I don't know exactly what e minus 1 is, so I'm going to write down e minus 1. This is perfectly acceptable. But now we get here. And I don't know if you remember this, right? You don't know how to handle when you have a variable in the exponent. You don't. You can't. What we've talked about in the past were patterns. Like, you know how to handle if it was 2 to the x, you know how to handle exactly if it's e to the x, because we've talked about that pattern. You know how to handle it if it's 3 to the x or 2 to the x or 5 to the x, because we did all the work with that pattern and we used that pattern. You don't know how to handle x to the x, right? You can't handle a variable in the exponent. The only reason you can handle it here is that we've dealt with it and created a pattern. You don't have a pattern for this. And when you don't have a pattern for this, right, you have to get the variable out of the exponent. And the only way to get the variable out of the exponent is take natural log of both sides. And then, so that's going to give me natural log of y is equal to, now with that natural log, that lets me bring my exponent down in front. And so that gives me x natural log x. Now, finish the problem. Everybody unraise your hand when you finish the problem, then raise your hand. All right, so take the derivative of both sides. Now the derivative of this side's easy. That's just going to be 1 over y dy dx. I've got to remember product rule on this side, so root of x is 1, so I get natural log of x, plus x times 1 over x. So I end up with 1 over y dy dx equals natural log of x plus 1. And dy dx is equal to natural log of x plus 1 times y, but we don't want y in our final answer, so end up with natural log of x plus 1 times whatever y equals, and y was x to the x. So this one was kind of sneaky, right? You had to use logarithmic differentiation. Here's the difference. When we did logarithmic differentiation before, it was to make something easier. You could do it the old way. In this case, you have to use logarithmic differentiation to actually take the derivative. If you don't take log of both sides, you can't take the derivative. Like if you tried to take the derivative of this the way I took the derivative of this, that's not right. Like you don't know how to handle a variable in the exponent, so you have to take log of both sides so that you can get the exponent down in front. All right, so this is exponential. Next, let's review what we know about logs. So in reviewing what we know about logs, let's see. So let's say I give you y equals natural log of x plus 1, and I say take the derivative. Well, derivative of that's pretty easy. It's just going to give me, copy the bottom down, and it's going to give us an x plus 1. Derivative of that goes on top. Actually, let me change that. Let's start with y equals natural log of x. And so the derivative of that is just 1 over x. We're going to start really basic. I need to come back to that, but right now we're going to start with, like, the derivative of natural log of x is just 1 over x, right? So this is log base e. How do we do it if I want y equals natural, I want y equals log base 2 of x? So if I ask you to find derivative of natural log of x, no problem. I basically gave you the pattern, we played around with the pattern, and we practice it a bunch. But how do you take the derivative of, log base 2 of x? And what I'm about to do is give the explanation of the pattern, and then I'm going to summarize the pattern. So what I'm about to write, you don't need to write. So you're not going to ever have to worry about creating it. But I'm the teacher, so I need to create it. The first thing I'm going to do is swoop, and so when I swoop the 2, that's going to give me 2 to the y is equal to x. That's step 1. Next, I look at this, and my goal here, I said find the derivative. That's, my goal is to find dy dx. Now, that looks cleaner, but I don't know how to handle it because I have a variable in the exponent. So what do? Well, what I do is take natural log of both sides because natural log lets me bring the exponent down in front. So I end up with y times natural log of 2 is equal to, well, I know the derivative of natural log of x ends up being 1 over x. Oh, whoops, whoa. I didn't take the derivative yet. And so now I take the derivative of both sides, so the derivative of y gives me dy dx times natural log of 2, and the derivative of this gives me 1 over x. And if I want to solve for dy dx, then I'm going to multiply times a 1 over natural log 2, 1 over natural log of 2, and so I end up with dy dx, or my derivative, is equal to 1 over x times natural log of 2. Actually, in practice, I usually write this as 1 over natural log of 2 times x. All right, so I want to compare these two. Now, there's all that work, and there's another way to do it about using change of base formula, but I'm not going to get into that. I want to look at what we know. I'm looking for patterns. The derivative of natural log of y is 1 over, derivative of natural log x is 1 over x. That's it. The derivative of log base 2x is 1 over x. Notice how this and this are exactly the same, but this, when you have a log base 2, we have this natural log of 2 in the bottom. Right? This is your adjustment. When you take the derivative of natural log, how you take the derivative of log base 2 is the exact same way you take the derivative of natural log. You do 1 over stuff times derivative of stuff. The difference is you're going to have an adjustment. So, example. If I give you y is equal to log base 3 of x squared plus 2x. And I want to compare that to y equals natural log of x squared plus 2x. I think it's very important to do the comparison. This is easy. Derivative of this, I'm going to copy this on the bottom. That's going to give me it's going to give me an x squared plus 2x. The derivative of that goes on top, which is going to give me a 2x plus 2. Right? So this is the derivative of natural log. Right? This is what we practiced basically all of last week. How do we take the derivative of log base 3? You do the same thing. Your derivative is going to be, we're going to create a fraction, copy this on the bottom, we're going to get x squared plus 2x. Take the derivative of that, stick it on top, that's going to give me a 2x plus 2. The difference is, because this is not base e, we need an adjustment. The adjustment is going to be natural log of 3, and the adjustment goes in the bottom. So when we compare these two, what I want you to get out of it is taking the derivative of this is pretty much the exact same thing as taking the derivative of this. You do the same thing. You copy the stuff on the bottom, you take the derivative of the stuff on the bottom, stick it on top, just like we did here. The difference is, because it's not base e, because it's log base 3, we need an adjustment. And our adjustment is going to be natural log of 3. All right? So, your turn. I want you to do these two problems. Problem number 1, y equals natural log of, y equals natural log of, we'll do it this way, sine x plus x squared. And I also want you to take the derivative of y equals log base 5 of sine x plus x squared. Yeah. So when everybody take the derivative of those two, write those down, and after you've written them down, do the electronic hand raise. All right. So, just like the other one, take the derivative of this, copy the stuff on the bottom, which is going to give me sine x plus x squared. The derivative of that I'm going to stick on top, which is going to give me cosine x plus 2x. Okay. Over here, my derivative, I'm going to do the exact same thing. Copy this stuff on the bottom, so I get sine x plus x squared. The derivative of that goes on top, which gives me cosine x plus 2x. The difference is there's an adjustment because it's not base e, it's base 5. And since it's base 5, I need to make sure I stick a natural log of 5 in the bottom. Oh, actually, we've been doing this all along. Right? I just want to point it out. See, what if we do the adjustment here? The adjustment is natural log of whatever the base is. Your base here is e, and so if I stick a natural log of e, I haven't really changed anything because natural log of e is just 1. Right? So, and the same thing is with the exponential functions. Technically, we've been doing the adjustment all along. The adjustment just happened to be natural log of e, which is 1. So, that's kind of our summary, right? So, let's get to some applications. Application number 1. Find the equation of the tangent line. So I want everyone to find the equation of a tangent line 2. Y is equal to 5 to the x minus 2 at the point 2, 1. So I want everybody to find the equation of the tangent line. After you've got your equation, after you got your line, do the electronic hand raise. All right. So, find an equation of a line. I need a slope and a point. Here's my point. Slope, that means I take the derivative. So, derivative of 5 to stuff is going to be 5 to stuff times derivative of stuff, which is just 1. But I need my adjustment, which is going to be natural log of 5. Now I need to plug in my values. So when I plug in, I'm going to plug in 2. That's going to be natural log of 5 times 5 to the 2 minus 2. Well, that's 0. 5 to 0 is 1. So I end up with the natural log of 5 as my answer. Forgot to put like a little parenthesis where I plugged in 2. So I take the derivative, plug in 2, and I end up with natural log of 5. Natural log of 5 is a number. Not a very nice number, but it's a number, and that's my slope. And so now to find my equation line, here's my slope, here's my point. So I get y minus 1 is equal to natural log of 5 times x minus 2. And believe it or not, I've seen them use this on a multiple choice question as recently as within the last 5 years. So making sure you know how to take the derivative of base other than e. It doesn't show up a lot, but it does show up. So that's why we're talking about it. All right, actually got, let's do one more. Actually, I have 2 more. I don't know if I'm gonna get to the second one. Next question. Find the equation of the tangent line. This time it's going to be y is equal to log base 10 of 2x at the point 5, 1. All right. So what do? Well, same thing. Find an equation of a line. There's a point. I need my slope. So I need to take the derivative. I see log of stuff. Well, see, log of stuff is copy stuff on the bottom. The derivative of stuff goes on top. Because this is not natural log, I need an adjustment. My adjustment for this is going to be natural log of 10. And so this whole thing, the 2's are going to cancel. It's going to give me 1 over natural log of 10 times an x. I'm interested in at the point 5, 1. So when x is 5, so when I plug in 5, that's going to give me 1 over natural log of 10 times 5. And that's my slope. So there's my slope. There's my point. And please don't say that's 50. Right? These are separate. In fact, if this was a problem in the textbook, I think they would probably have this written out as 1 over 5 times natural log of 10 to avoid the confusion, is that 5 inside the natural log or not? So that's my slope. Then I'll have x minus 5, and I'll have y minus 1. And so my equation, right, there's my point, and this ugly number is your slope. I mean, get used to seeing slopes that look like that. All right. We've got time for one more. I'm actually kind of curious how you handle it. So I'm going to start with y is equal to 1 plus x to the x. Open to suggestions. What is your first step when you see this? And you've got to take the derivative.
Natural log both sides?
Yeah. You've got to take natural log of both sides. Okay? Because anytime you see a variable in the exponent, you can't handle it. Okay, so I take natural log of both sides. I get natural log of y equals x, natural log of 1 plus x. Derivative of this ends up being 1 over y, dy dx. I got to use product rules, so that's going to give me natural log of 1 plus x plus, it's like x times 1 over x plus 1. End up with dy over dx equals natural log of 1 plus x over x plus 1. All that times y, but since y is equal to this, I end up with 1 plus x to the x. And there's our answer. All right. Homework's out of your book. It's a bunch of practice.